Hello everyone. As promised in the previous video on infrared spectroscopy, we are back with another exciting and informative video on NMR spectroscopy. Thanks again for supporting the second video of the series on spectroscopy. Your likes, shares and subscriptions are highly appreciated. From your response, it is very clear that interaction method or question-answer method is better than many other methods of learning. This is a long video. Please watch the entire video to learn all aspects of NMR spectroscopy. You can learn the topic clearly only if you watch this video till end. Let's start. The topic of the video is Nuclear magnetic resonance spectroscopy or proton magnetic resonance spectroscopy. The first question is, what is the full form of NMR spectroscopy? Name the scientists who discovered NMR spectroscopy. The answer to this question is, the full form of NMR spectroscopy is nuclear magnetic resonance spectroscopy. Nuclear magnetic resonance spectroscopy was discovered by two independent groups, Felix Bloch and Edward Purcell in 1946. Both these scientists received the Nobel Prize in Physics in 1952 for their discoveries. The next question is question number 2. What is the simplest type of NMR spectroscopy? Explain in detail. The answer to this question is, the simplest type of NMR spectroscopy is proton NMR, 1H NMR. It specifically observes the behavior of hydrogen nuclei, protons, in a sample. In proton NMR spectroscopy, the sample is placed in a strong magnetic field and the nuclei are irradiated with radiofrequency radiation. The protons absorb energy and undergo transitions between different nuclear spin states. One of the state will have lower energy and is called ground state or normal state. The other state will have higher energy and is called excited state. The resulting spectrum provides information about the number of hydrogen atoms in different environments within the molecule, as well as their connectivity or how they have bonded to each other. The chemical shift, spin-spin coupling, and the area under the peak in the nuclear magnetic spectrum help in determining the structure of the compound. The next question is question number 3. Why is NMR spectroscopy considered better than ultraviolet spectroscopy and infrared spectroscopy? The answer to this question is, NMR spectroscopy is considered superior to ultraviolet spectroscopy and infrared spectroscopy due to many reasons. Some of these are as follows. The first reason is, NMR spectroscopy provides much better details for molecular structure determination. Unlike ultraviolet and infrared spectroscopies, the NMR spectroscopy provides much detailed information about the molecular structure, including connectivity of atoms and the three-dimensional arrangement of atoms. The second reason is, NMR spectroscopy is non-destructive in nature. NMR spectroscopy is generally non-destructive, whereas ultraviolet or infrared spectroscopy may cause some changes to sensitive samples. NMR spectroscopy or PMR spectroscopy is highly specific. NMR spectroscopy offers high specificity regarding chemical environments of nuclei, especially protons or carbon atoms. As a result of this, NMR spectroscopy becomes more informative for studying organic compounds than ultraviolet or infrared spectroscopy. The third reason is NMR spectroscopy can also be used for the quantitative analysis. NMR spectroscopy, unlike the ultraviolet and the infrared spectroscopies, provides quantitative information with respect to the relative number of atoms in different environments. The next question is question number 4. How is NMR spectroscopy different from ultraviolet visible spectroscopy and infrared spectroscopy? The answer to this question is, the first difference lies in the principles of these spectroscopies. Principle: NMR spectroscopy is based on the absorption of radiofrequency radiation by atomic nuclei in a magnetic field, while ultraviolet visible spectroscopy is based on the absorption of ultraviolet or visible light, and infrared spectroscopy involves the absorption of infrared light by molecular vibrations. The second difference is with respect to the extent of information provided. NMR spectroscopy provides much better and more detailed information about the chemical structure, types of bonding, and dynamics of molecules, whereas ultraviolet visible mainly provides electronic transition information, and infrared gives insights into molecular vibrations and functional groups. The third difference is with respect to the resolution. NMR spectroscopy offers higher resolution in structural determination, providing more specific molecular details, whereas ultraviolet and infrared spectroscopy are often used for identifying presence of unsaturation and specific functional groups or electronic transitions. The next question is question number 5. Which part of the atom is involved in the study of NMR spectroscopy? The answer to this question is, NMR spectroscopy involves the nucleus of an atom, specifically nuclei with an odd number of protons or neutrons, which poses a magnetic moment and spin, such as hydrogen 1H, or carbon-13, C13. The next question is question number 6. Can nuclei of all atoms and their isotopes participate in NMR spectroscopy? If not, then why? The answer to this question is, no, nuclei of all atoms and their isotopes cannot participate in NMR spectroscopy. Only those nuclei which have a non-zero nuclear spin, which means nuclei for which the nuclear spin quantum number is not equal to 0, are NMR active. This can be decided very easily. The nucleus with an odd number of protons, neutrons, or both. Nuclei with an even number of both protons and neutrons, such as C12 or O16, have a nuclear spin quantum number of 0 and cannot be studied by NMR. The next question is question number 7. Some nuclei are NMR active, whereas others are not. What are the bases for deciding whether a nucleus will be NMR active or not? The answer to this question is, the activity of a nucleus in NMR depends on its nuclear spin quantum number, I. Nuclei with a non-zero spin quantum number, I, greater than 0, are NMR active. These include isotopes like 1H, C13, F19, and P31. Nuclei with a spin quantum number of 0 are NMR inactive, like C12 and O16, because they lack a magnetic moment or have value of magnetic moment equal to 0. You can easily find whether a nucleus will be NMR active or not by looking at the atomic number and mass number of the nucleus. If both of these are even, then the nucleus will be NMR inactive. On the other hand, if any one of these or both of the two quantities, that is, atomic number and atomic mass, are odd, then the nucleus will be NMR active. The next question is question number 8. Give examples of NMR active nuclei and NMR inactive nuclei. The answer to this question is NMR active nuclei, proton or hydrogen nucleus or hydrogen atom, because its atomic number and mass number, both, are odd. C13 or carbon-13 is also NMR active. No doubt, its atomic number is even, but its mass number is odd. Similarly, N15, nitrogen-15, F19, fluorine-19, and P31, phosphorus-31, are the other examples of NMR active nuclei or atoms. All these are NMR active because their atomic numbers and mass numbers, both, are odd numbers. NMR inactive nuclei. The examples of NMR inactive atoms or nuclei are C12, carbon-12, O16, oxygen-16, S32, sulfur-32, and many more. You can see their atomic numbers and mass numbers, both, are even numbers. The next question is question number 9. What is meant by the term nuclear spin quantum number? What is its importance? The answer to this question is the nuclear spin quantum number, generally represented with alphabet I, is a value that describes the angular momentum of a nucleus due to its spin. It is important because it determines whether a nucleus will have a magnetic moment or not, and therefore whether it will be NMR active or NMR inactive. Nuclei with non-zero spin, I, is not equal to 0, have magnetic moments and can interact with an external magnetic field, which forms the basis of NMR spectroscopy. The next question is question number 10. What do you mean by nuclear spin states? Explain with the help of 3 examples. The answer to this question is nuclear spin states are the possible orientations of a nucleus's magnetic moment in the presence of a magnetic field. For example, 1H, proton, it has a spin quantum number of 1 by 2, so it has 2 spin states, plus 1 by 2 and minus 1 by 2. C13, carbon-13, also has a spin quantum number of 1 by 2 with 2 spin states, plus 1 by 2 and minus 1 by 2. N14, nitrogen-14, has a spin quantum number of 1, so it has 3 spin states, plus 1, 0 and minus 1. The next question is question number 11. What do you mean by the word degenerate? The answer to this question is the term degenerate refers to states that have the same energy. In NMR spectroscopy, nuclear spin states are degenerate, have equal energy in the absence of an external magnetic field. This means they will have same energy associated with them. The next question is question number 12. Are nuclear spin states of any NMR nucleus degenerate or not? Also explain when will these be degenerate and when they will not. The answer to this question is we cannot say unless we know whether the nucleus is under the influence of external magnetic field or not. Secondly, we must also know whether the nuclear spin quantum number is 0 or non-zero. In case of atoms or nuclei with 0 value of nuclear spin quantum number, different nuclear spin states will be degenerate in the absence or in the presence of external magnetic field. Nuclear spin states of the nuclei having non-zero values of the magnetic spin quantum number will be degenerate in the absence of an external magnetic field because they will have the same energy. However, when an external magnetic field is applied, the degeneracy is lifted and the spin states split into different energy levels depending on the strength of the field. The next question is question number 13. How many nuclear spin states are shown by the proton or the hydrogen nucleus? The answer to this question is, we know that the proton or the hydrogen atom is NMR active because both atomic number and mass number are odd. Proton or hydrogen nucleus has a spin quantum number of 1/2. This means it is doubly degenerate. So, it shows two spin states, +1/2, aligned with the magnetic field, and -1/2, opposed to the magnetic field. The next question is question number 14. What happens to the nuclear spin states of a proton or hydrogen nucleus when we keep it in an external magnetic field? Explain in detail. The answer to this question is, when a proton is placed in an external magnetic field, its two spin states, +1/2 and -1/2, split into two different energy levels due to the interaction with the external magnetic field applied. The +1/2 state, aligned with the external magnetic field, has lower energy, and the -1/2 state, opposed to the external magnetic field, has higher energy. The energy difference between these states depends on the strength of the magnetic field. The next question is question number 15. What is the effect of strength or intensity of the external magnetic field on the gap between the nuclear spin states of a proton or hydrogen nucleus? Explain in detail. The answer to this question is, the energy gap between the two nuclear spin states is directly proportional to the strength or the intensity of the external magnetic field. It means that the energy gap increases as the strength or the intensity of the external magnetic field increases. This is because the magnetic interaction between the proton's magnetic moment and the external field becomes stronger, leading to a greater energy difference between the aligned +1/2 and opposed -1/2 states. The next question is question number 16. What is meant by precessional motion? Explain it in detail by taking at least 2 examples. The answer to this question is, precessional motion refers to the movement of a spinning nucleus in a magnetic field, where its axis of spin traces out a cone-like shape. This motion is similar to the wobbling motion of a spinning top under gravity. In NMR, protons placed in an external magnetic field experience precession, and the frequency of this precession, called the Lama frequency, depends on the magnetic field strength. Example 1. A proton in a magnetic field precesses around the direction of the external magnetic field at a specific frequency depending on the strength of the external magnetic field. Example 2. Carbon-13 nuclei in an external magnetic field also exhibit precessional motion, but at a different frequency than protons due to their different magnetic properties. The next question is question number 17. What is meant by gyromagnetic ratio? What is its value for a proton or hydrogen nucleus? What is its significance? Explain in detail. The answer to this question is, the gyromagnetic ratio, often represented with the Greek letter gamma, is the ratio of the magnetic moment of a nucleus to its angular momentum. It is a fundamental property of the nucleus that determines the frequency at which the nucleus precesses under the influence of the external magnetic field, also known as the Larmor frequency. For a proton, 1h, the gyromagnetic ratio is approximately 26,752 radians per Tesla per second or 42.58 MHz per Tesla. Significance: the gyromagnetic ratio is crucial in NMR spectroscopy because it directly determines the resonance frequency of a nucleus in a magnetic field. The resonance condition, which is necessary for NMR to occur, depends on the product of the gyromagnetic ratio and the external magnetic field strength. The next question is question number 18. What is the principle of nuclear magnetic resonance spectroscopy? Explain in detail. The answer to this question is, the principle of nuclear magnetic resonance, NMR, spectroscopy is based on the interaction between nuclear magnetic moments and an external magnetic field. Nuclei with non-zero nuclear spin quantum number values poses a magnetic moment that can align with or against an applied magnetic field, creating distinct energy levels. Those which are aligned with the external magnetic field will have the lower energy and will form the ground state. On the other hand, if the magnetic moment aligns against the external magnetic field, they will give rise to energy states that will have higher energies and will form the excited energy state. The two states differ by a fixed energy gap, which depends upon the strength of the external magnetic field acting on the nuclei. When the sample is exposed to radiofrequency radiation that matches the energy gap between these levels, nuclei absorb the energy and transition between spin states takes place. This absorption produces an NMR signal which can be detected and analyzed to provide detailed information about the chemical structure and environment of the atoms in the sample. The next question is question number 19. How much will be the energy gap between the different nuclear spin states of hydrogen when we keep it in an external magnetic field? The energy gap, delta E, between the nuclear spin states of hydrogen, 1H, nucleus in an external magnetic field is given by the formula. Delta E is equal to H upon 2 pi multiplied by gamma multiplied by B0. Where delta E is the energy gap. Gamma is the gyromagnetic ratio of the proton, 42.58 MHz per Tesla. B0 is the strength of the external magnetic field. H upon 2 pi is the reduced Planck's constant. The value of H is equal to 6.626 into 10 raised to power minus 34 joule second. The exact value of the energy gap depends on the strength of the external magnetic field. The next question is question number 20. Write the formula showing the relationship between energy required, gyromagnetic ratio, and strength of external magnetic field. The answer to this question is, the formula that shows the relationship between the energy, delta E, required for a nuclear spin transition, the gyromagnetic ratio, gamma, and the external magnetic field strength, B0, is delta E is equal to H upon 2 pi multiplied by gamma multiplied by B0. Where delta E is the energy gap, gamma is the gyromagnetic ratio, B0 is the strength of the external magnetic field, H upon 2 pi is the reduced Planck's constant. The next question is question number 21. What is the reason for the origin of the signal in PMR spectrum, proton magnetic resonance spectrum? Explain in detail. The answer to this question is, the origin of the signal in PMR spectrum, proton magnetic resonance spectrum, can be explained as the signal arises from the absorption of radiofrequency radiation by the protons, 1H nuclei, when they undergo transition between different nuclear spin states in the presence of an external magnetic field. In the absence of a magnetic field, the nuclear spin states are degenerate, have the same energy. However, when a magnetic field is applied, the proton's spin states split into two energy levels. When radiofrequency radiation corresponding to the energy difference between these states is applied, the protons absorb the energy and move from the lower energy state to the higher energy state, producing an NMR signal. The next question is question number 22. What is the name of the instrument used for recording nuclear magnetic resonance spectrum? What are different types of such instruments? Explain these in detail. The answer to this question is, the instrument used for recording nuclear magnetic resonance spectra is called an NMR spectrometer. There are two main types of NMR spectrometers. 1. Continuous wave CW spectrometers. In these instruments, the frequency of the radio frequency RF radiation is held constant while the magnetic field is varied. The resonance condition is achieved when the energy of the RF matches the energy gap between nuclear spin states. 2. Fourier transform FT spectrometers. These instruments use a pulse of radio frequency radiation containing a range of frequencies to excite all nuclei at once. The response, free induction decay, is recorded and the signal is processed using Fourier transformation to generate a spectrum. FT NMR is much faster and more sensitive than CW-NMR, and it is the preferred method in modern NMR spectroscopy. The next question is question number 23. Explain all the parts of a continuous wave type spectrometer. The answer to this question is, a continuous wave CW spectrometer consists of the following parts. 1. Magnet. It is used to create a strong, uniform magnetic field to align nuclear spins. 2. Radio frequency RF generator. It produces a continuous wave of RF radiation. 3. Sweep generator. It varies the magnetic field or radio frequency RF radiations to scan through the resonance conditions. 4. Detector. It monitors the absorption of RF radiation as the magnetic field or RF frequency is varied. 5. Sample holder. It contains the sample being studied. 6. Amplifier. It enhances the strength of the weak NMR signals for better detection. 7. Readout device. It displays the resulting NMR spectrum. The next question is question number 24. What are the characteristics of a solvent that can be used for preparing the sample of the substance to be analyzed with the help of PMR spectroscopy? Explain in detail. The answer to this question is, a solvent used in PMR spectroscopy must have the following characteristics. NMR inactivity. The solvent should not contain any protons that could produce signals in the NMR spectrum. Therefore, deuterated solvents, example CdCl3d2O, C6d6 and similar other solvents, are used because deuterium, 2H, does not produce signals in the proton NMR region. Low viscosity, to avoid broadening of NMR signals and to ensure sharp, well-resolved peaks. Chemical inertness, the solvent should not react with the sample. Solubility, the sample must dissolve completely in the solvent for a good spectrum to be obtained. The next question is question number 25. Why do we obtain many signals in a PMR spectrum? The answer to this question is, multiple signals are obtained in a PMR spectrum because different hydrogen atoms in a molecule experience different chemical environments. Each unique chemical environment causes a different shielding effect or deshielding effect, which leads to different resonance frequencies, chemical shifts for the protons. These variations in the local magnetic environment result in distinct signals for each set of chemically distinct protons. The next question is question number 26. Why do different hydrogen atoms absorb different energies for making a transition from a lower energy nuclear spin state to a higher energy nuclear spin state? The answer to this question is, different hydrogen atoms absorb different energies for nuclear spin transitions due to differences in their chemical environments. The electron cloud around each proton can either shield or deshield the nucleus from the external magnetic field, affecting the local magnetic field that the proton experiences. As a result, the energy gap between the spin states varies, leading to different resonance frequencies and therefore different energy absorption. The next question is question number 27. What do you mean by equivalent protons and non-equivalent protons? Explain with the help of examples. The answer to this question is, equivalent protons are the protons in a molecule that have the same chemical environment and, therefore, produce the same signal in the NMR spectrum. For example, the three protons in a methyl group, CH3, are equivalent and produce a single signal. Non-equivalent protons are protons that have different chemical environments and produce separate signals. For example, in ethanol, CH3CH2OH, the protons of the methyl group, CH3, are non-equivalent to those in the methylene group, CH2. The next question is question number 28. Justify the statement that magnetically equivalent protons are chemically equivalent protons. The answer to this question is, magnetically equivalent protons experience the same magnetic field and have the same spin-spin coupling with neighboring nuclei. If protons are chemically equivalent, i.e., in the same chemical environment, they are also magnetically equivalent because they behave the same way in an external magnetic field and couple similarly with nearby protons. For example, the protons in a methyl group, CH3, are both chemically and magnetically equivalent. The next question is question number 29. How will you calculate the number of signals that can be obtained while recording a PMR spectrum? Explain with the help of some examples. The answer to this question is, the number of signals in a PMR spectrum depends on the chemical equivalence of the protons. Protons in the same chemical environment give one signal, while non-equivalent protons give separate signals. The answer to this question is, example 1, in methane, CH4, all four protons are equivalent, so there is one signal. Example 2, in ethanol, CH3CH2OH, the three protons in the CH3 group and the two protons in the CH2 group are non-equivalent, resulting in two separate signals. To calculate the number of signals, analyze the symmetry and chemical environment of each set of protons in the molecule. The next question is question number 30. Give 5 examples to understand the concept of the number of signals obtained in a PMR spectrum. The answer to this question is 1. Methane, CH4, all 4 protons are equivalent, so there is only one signal in the PMR spectrum. 2. Ethyl alcohol, CH3CH2OH. The protons in the CH3 group are equivalent, and the CH2 protons are equivalent but different from the CH3 protons. This gives 3 signals, one for CH3, one for CH2, and one for the OH proton. 3. 1. To dichloroethane, ClCH2CH2Cl, both methylene groups, CH2, are equivalent, so only one signal is observed. 4. To butene, CH3CH double bond CHCH3, the two CH3 groups are equivalent, and the two vinylic protons, H attached to C double bond C, are equivalent. This gives two signals, one for the CH3 protons and one for the vinylic protons. 5. Toluene, C6H5CH3, the protons in the methyl group, CH3, are equivalent, while the protons in the benzene ring, C6H5, appear as different signals due to their positions relative to the methyl group. This gives 4 signals. The next question is question number 31. What do you understand by enantiotopic protons? Explain in detail by taking at least 5 examples. The answer to this question is, enantiotopic protons are 2 or more protons in a molecule that are related by a infrared plane but not identical. They appear chemically equivalent in a natural environment but become chemically non-equivalent in a chiral environment, leading to different signals in NMR spectroscopy if a chiral reagent or environment is present. Examples: 1. Chloromethane, CH3Cl. The 3 protons are equivalent but in a chiral environment, they can behave differently. 2. 1. 1. To trichloroethane, ClCH2CHCl2. The two CH2 protons are enantiotopic because replacing either one with a different group, example deuterium, would give enantiomers. 3. Cyclohexane, C6H12. Protons on carbons that are equatorial or axial positions in a chair conformation can be enantiotopic.
4. 2-butanol, CH3CH, OH, CH2CH3. The protons on the CH2 group adjacent to the OH are enantiotopic.
5. Propionic acid, CH3CH2COOH. The 2 protons on the CH2 group are enantiotopic due to the adjacent chiral center. The next question is question number 32. Only the number of signals in PMR spectroscopy can be used to differentiate many pairs of compounds. Justify this statement by taking some examples. The answer to this question is, the number of signals in a PMR spectrum provides valuable information about the symmetry and distinct chemical environments of protons in a compound. This property can be used to differentiate compounds. Examples: 1. Propane, CH3CH2CH3 versus butane, CH3CH2CH2CH3. Propane gives 2 signals, one for the CH3 group and one for the CH2, while butane gives 3 signals due to the different environments of the central and terminal CH2 groups. 2. Ethanol, CH3CH2OH versus dimethyl ether, CH3OCH3. Ethanol has 3 signals for the CH3, CH2, and OH protons, while dimethyl ether has 1 signal for the equivalent CH3 groups. 3. Cyclohexane, C6H12, in different conformations, chair and boat conformations will result in different numbers of signals due to the different environments of the axial and equatorial protons. The next question is question number 33. Explain the terms shielding and deshielding with reference to PMR spectroscopy in detail. The answer to this question is shielding. Shielding occurs when the electron cloud around a proton partially opposes the external magnetic field, reducing the effective magnetic field experienced by the proton. Shielded protons resonate at higher magnetic field strengths, upfield, lower chemical shifts. Deshielding. Deshielding occurs when electron withdrawing groups or electronegative atoms reduce the electron density around a proton, making the proton experience a stronger effective magnetic field. Deshielded protons resonate at lower magnetic field strengths, downfield, higher chemical shifts. The next question is question number 34. How will you determine the position of signals for different types of protons? Explain in detail. The answer to this question is, the position of signals for different types of protons in NMR spectroscopy is determined by their chemical shift, which is influenced by the electronic environment surrounding the protons. Electron-donating groups, shielding effect, protons near electron-donating groups, example alkyl groups, experience more electron density, leading to upfield shifts, lower chemical shift values. Electron withdrawing groups, deshielding effect, protons near electron withdrawing groups, example halogens, carbonyl groups, experience reduced electron density, leading to downfield shifts, higher chemical shift values. Aromatic and alkyne systems, protons in these environments experience anisotropic effects that shift their signals upfield or downfield depending on their position relative to the P system. The next question is question number 35. Explain in detail the factors responsible for shielding of protons. The answer to this question is factors responsible for shielding. 1. Electron-donating groups, example alkyl groups, these increase electron density around protons, causing shielding and upfield shifts. 2. Nearby lone pairs of electrons, lone pairs from atoms like oxygen or nitrogen can contribute to electron density and thus increase shielding. 3. Aromatic rings in specific positions, protons situated inside the ring current of an aromatic system can experience shielding. The next question is question number 36. Explain in detail the factors responsible for deshielding of protons. The answer to this question is factors responsible for deshielding. 1. Electron withdrawing groups, example halogens, carbonyls, these reduce electron density around protons, leading to deshielding and downfield shifts. 2. Electronegative atoms, atoms like oxygen, nitrogen, or halogens pull electron density away from the proton, deshielding it. 3. Aromatic rings, outside the ring current, protons located near but outside an aromatic ring experience deshielding due to the induced magnetic field of the ring. The next question is question number 37. Explain the electromeric effects for shielding and deshielding of protons in PMR spectroscopy? The answer to this question is, the electromeric effect refers to the transfer of electron density between atoms, or groups, which influences proton shielding. Electron-donating groups, positive electromeric effect, cause shielding by increasing the electron density around the proton, leading to upfield shifts. Electron-withdrawing groups, negative electromeric effect, cause deshielding by decreasing electron density around the proton, leading to downfield shifts. The next question is question number 38. What do you mean by anisotropic effects for shielding and deshielding of protons in PMR spectroscopy? Explain in detail with the help of two examples. The answer to this question is, anisotropic effects occur when p electrons in systems like aromatic rings or triple bonds create a local magnetic field that affects nearby protons. 1. Aromatic rings, protons positioned outside the ring's p-electron cloud experience deshielding, downfield shift, while protons inside the ring current are shielded, upfield shift. Example, in benzene, the ring current deshields the protons on the ring, causing them to appear downfield, around 7 to 8 ppm. 2. Triple bonds, alkynes, protons attached to sp hybridized carbons experience shielding due to the anisotropy of the triple bond. Example, in alkynes, terminal protons resonate upfield, around to -3 ppm, due to shielding from the electron cloud. The next question is question number 39. Which substance is generally used as a reference while recording the PMR spectrum? Why has this been selected as a reference? Explain in detail. The answer to this question is, tetramethylsilane, TMS, is used as the reference in PMR spectroscopy because it has 12 equivalent protons that give a sharp, single signal. TMS is chemically inert and does not interact with most samples. The signal appears at 0 ppm, far upfield, making it easy to distinguish from sample peaks. The next question is question number 40. What is chemical shift in PMR spectroscopy? Explain in detail. What are the units of chemical shift? How do we calculate chemical shift in PMR spectroscopy? The answer to this question is, chemical shift, delta, is the difference in resonance frequency of a proton compared to a reference, usually TMS, in a magnetic field. It reflects the electronic environment of the proton and is influenced by shielding and deshielding effects. Units, the chemical shift is expressed in parts per million, ppm. Formula. Delta is equal to new sample minus new reference divided by new reference multiplied by 10 raised to the power 6. Where delta is equal to chemical shift in ppm. New sample is equal to resonance frequency of the sample. New reference is equal to resonance frequency of the reference, TMS. The next question is question number 41. How many scales do we have for noting or measuring the chemical shift? What is the relationship between these scales? The answer to this question is, there are two main scales used for measuring chemical shift. 1. Delta scale, measured in ppm, with TMS set to 0 ppm. 2. Tau scale, used less commonly, with 10 delta representing the value in the tau scale. The relationship between the two scales is tau is equal to 10 delta. The next question is question number 42. Which scale out of the two scales for measuring the chemical shift is considered better, and why? The answer to this question is, the delta scale is considered better because it is easier to understand as higher numbers correspond to deshielding, downfield, and lower numbers to shielding, upfield. It is universally adopted and consistent with modern NMR instruments. The next question is question number 43. Make a list of chemical shifts for most common types of protons in organic compounds. The answer to this question is, here is a general list of typical chemical shift values, delta in ppm, for different types of protons in organic compounds. Alkene protons, CH3, CH2, 0.8 to 1.5 ppm. Alkyl halide protons, CH2X, where X can be Cl, Br, I, 3.0 to 4.5 ppm.
Alcohol protons OH 1, 0 to 5 ppm depends on hydrogen bonding.
Ether protons, CH2O, 3.3 to 4.0 ppm. Aromatic protons, on benzene ring, 6.5 to 8.5 ppm. Aldehyde protons, CHO, 9.0 to 10.0 ppm. Carboxylic acid protons, COOH, 10.0 to 12.0 ppm. Alkyne protons, C triple bond CH, 1.7 to 3.1 ppm. Alkene protons are CH double bond CH2, 4.5 to 6.5 ppm. Amine protons, NH2, NH, 1.0 to 5.0 ppm. Amide protons, CONH2, 6.0 to 8.0 ppm. The next question is question number 44. Explain inductive effects responsible for chemical shifts. The answer to this question is, the inductive effect occurs when electronegative atoms, or groups, example halogens, oxygen, nitrogen, pull electron density away from the proton through sigma bonds, reducing electron shielding, and causing a downfield shift, higher d value. Example, in halogenated compounds like CH3Cl, the chlorine atom exerts an electron withdrawing inductive effect, causing the attached protons to experience reduced electron shielding and resonate at a higher d value compared to methane, CH4. The next question is question number 45. Explain anisotropic effects responsible for chemical shifts. Anisotropic effects arise from the local magnetic fields created by p electrons in unsaturated systems such as double bonds, triple bonds, and aromatic rings. These effects lead to shielding or deshielding depending on the position of the protons relative to the induced field. Aromatic systems, protons on the periphery of an aromatic ring experience deshielding and appear downfield around 7 to 8 ppm. Alkyne systems, protons attached to sp hybridized carbons, C triple bond C, are shielded due to the anisotropic field and resonate upfield around to 2-3 ppm. The next question is question number 46. How are chemical shift and hydrogen bonding related? Explain in detail. The answer to this question is, hydrogen bonding can significantly influence the chemical shift of protons, especially those in hydroxyl, OH, amine, NH2, and carboxylic acid, COOH, groups. The formation of hydrogen bonds typically leads to deshielding, Hydrogen-bonded protons experience less electron density due to interactions with the electronegative atom they are bonded to, or other molecules. This results in a downfield shift, higher delta value. For example, the proton of a hydroxyl group, OH, in an alcohol that is hydrogen-bonded can show chemical shifts in the range of 2 to 5 ppm, compared to non-hydrogen bonded alcohols that might resonate at lower values. The next question is question number 47. How can PMR spectroscopy be used to distinguish between alkanes, alkenes, and alkynes? The answer to this question is, PMR spectroscopy can distinguish between alkanes, alkenes, and alkynes based on the chemical shifts and coupling patterns of the protons. Alkanes, protons in alkanes typically resonate in the range of 0.8 to 1.5 ppm due to the high shielding by electron density around the carbon-hydrogen bonds. Alkenes, protons attached to double bonds, C double bond C, resonate between 4.5 and 6.5 ppm because of the deshielding effect of the sp2 hybridized carbons. Alkynes, protons attached to triple bonds, C triple bond C, resonate between 1.7 and 3.1 ppm due to shielding by the p-electron system. The distinct chemical shifts allow for clear differentiation between these types of compounds. The next question is question number 48. How will you calculate the number of protons of a particular type that are present in an organic compound? The answer to this question is, the number of protons of a particular type in an organic compound can be calculated using the integration of the peaks in a PMR spectrum. The area under each peak is proportional to the number of protons contributing to that signal. Steps 1. Identify the signals. Each distinct chemical environment for the protons produces a separate signal. 2. Measure the relative integration. The integral of each signal corresponds to the ratio of protons in that environment. 3. Determine the proton ratio. Compare the integration values to determine the relative number of protons in each environment. 4. Use molecular formula. Combine the proton ratio with the known molecular formula of the compound to assign the exact number of protons to each signal. The next question is question number 49. What is meant by peak area and what is its importance? Explain in detail. The answer to this question is, the peak area in any PMR spectrum represents the number of protons contributing to that particular signal. The integration of the peak area is directly proportional to the number of protons in a specific chemical environment. Importance: it helps in determining the relative number of protons in different environments within a molecule. By comparing the areas under different peaks, one can deduce the proton ratios in the compound, aiding in structure determination. For example, if the integration ratio of two peaks is 3:1, this suggests that one set of protons corresponds to 3 protons, example ACH3 group, while the other corresponds to 1 proton, example ACH group. The next question is question number 50. What will be the structure of peaks obtained in PMR spectroscopy? The answer to this question is, the structure of peaks in PMR spectroscopy is influenced by spin-spin coupling between the neighboring protons, leading to splitting patterns. This splitting follows the n+1 rule, where n is the number of neighboring protons and the peak splits into n+1 lines. Common splitting patterns. Singlet, no neighboring protons, there will be only one peak or single peak. Doublet, one neighboring proton, there will be 2 peaks of equal intensity. Triplet, 2 neighboring protons, there will be 3 peaks with a 1:2:1 intensity ratio. Quartet, 3 neighboring protons, there will be 4 peaks with a 1:3:3:1 intensity ratio. Multiplet, multiple neighboring protons, leading to complex splitting patterns. For example, in ethanol, CH3CH2OH. The CH3 group shows a triplet due to 2 neighboring CH2 protons. The CH2 group shows a quartet due to 3 neighboring CH3 protons. The OH group usually appears as a singlet due to rapid exchange with protons in solution. The next question is question number 51. What is the reason for the splitting of a peak in the PMR spectrum? Explain in detail. The answer to this question is, the splitting of a peak in PMR spectroscopy occurs due to spin-spin coupling between neighboring, non-equivalent protons. Protons on adjacent carbon atoms can interact through the bonds and influence each other's magnetic environment. This interaction causes the magnetic field experienced by one proton to vary depending on the spin states of the neighboring protons, leading to multiple closely spaced peaks instead of a single peak. If a proton has n neighboring, non-equivalent protons, its signal will split into n+1 peaks, a phenomenon known as the n+1 rule. For example, the CH3 group in ethanol shows a triplet because it is adjacent to 2 CH2 protons. The next question is question number 52. What do you mean by spin-spin coupling? What is its significance? Explain in detail. The answer to this question is, spin-spin coupling refers to the interaction between the magnetic fields of neighboring, non-equivalent protons. When 2 or more protons are close to each other, typically on adjacent atoms, their magnetic spins can affect one another, leading to splitting of NMR signals. Significance of spin-spin coupling. It provides structural information about how many protons are near each other and helps determine the connectivity of atoms within the molecule. It reveals the number of neighboring protons and how these protons are arranged around a central carbon atom. For instance, in ethanol, CH3CH2OH, the CH2 protons couple with the CH3 protons, leading to a quartet and triplet splitting pattern. The next question is question number 53. What are the rules for spin-spin splitting of proton signals in PMR spectroscopy? Explain in detail. The answer to this question is, the key rules for spin-spin splitting of proton signals in PMR spectroscopy are 1. N+1 rule. A proton will split into n+1 peaks, where n is the number of neighboring protons on adjacent atoms. For example, a proton adjacent to 2 protons will give rise to a triplet, 3 peaks. 2 equivalent protons do not split each other. Protons that are chemically equivalent in the same environment do not cause splitting of each other's signals. 3 coupling constants, J values. The distance between the split peaks is constant for coupled protons and is measured in Hertz, referred to as the coupling constant, J. 4 Pascal's triangle. The relative intensities of the split peaks follow the pattern of Pascal's triangle. Example, 1:1 for a doublet, 1:2:1 for a triplet, etc. The next question is question number 54. What is coupling constant? What is its significance? Explain in detail. The answer to this question is, the coupling constant, J, is the measure of the strength of the interaction, coupling, between two neighboring protons in PMR spectroscopy. It is defined as the separation between the peaks in a split signal and is measured in Hertz. Significance. It provides information about the distance and relationship between coupled protons. A large J value indicates strong coupling, while a small J value suggests weak coupling. It helps in identifying geometrical isomers and distinguishing between different types of bonds. Example, cis trans isomers often have different J values. The next question is question number 55. What are different types of subpeaks in which a peak can be split or divided? Explain in detail. The answer to this question is, the different types of subpeaks resulting from spin-spin splitting are named based on the number of peaks formed. Singlet, no splitting, a single peak. Doublet, two peaks, from coupling with one adjacent proton. Triplet, three peaks, from coupling with two adjacent protons. Quartet, four peaks, from coupling with three adjacent protons. Multiplet, complex splitting pattern from coupling with more than three protons, or multiple non-equivalent protons. The next question is question number 56. How will you find the intensities of subpeaks of a peak in PMR spectroscopy? Explain in detail. The answer to this question is, the relative intensities of subpeaks follow a specific pattern based on the number of neighboring protons and are given by Pascal's triangle. The intensity ratio for each subpeak is determined by the binomial distribution. For example, a doublet has an intensity ratio of 1:1. A triplet has an intensity ratio of 1:2:1. A quartet has an intensity ratio of 1:3:3:1. These intensity patterns help identify the number of adjacent protons. The next question is question number 57. In PMR spectroscopy, we observe that even subpeaks are further split. Explain this with the help of some examples. The answer to this question is, this phenomenon, known as complex coupling, occurs when protons are coupled to non-equivalent protons. Each set of non-equivalent protons causes splitting of the signal, resulting in further division of subpeaks. Example, in ethyl bromide, CH3CH2Br, the protons on the CH2 group are split into a quartet by the CH3 group, triplet splitting, and then each line of the quartet can be further split into a doublet due to coupling with the bromine nucleus, since Br has two isotopes. The next question is question number 58. Make a list of magnitudes of coupling constant for different cases of spin-spin coupling. The answer to this question is, here are some typical values for coupling constants, J values. Germinal coupling, within the same carbon, CH2, 10 to 16 Hz. Vicinal coupling, 3-bond, CH-CH, 7 to 10 Hz, for normal alkanes, 0 to 3 Hz, for cis alkenes, 6 to 15 Hz, for trans alkenes. Long-range coupling, 4-bond, or more, 1 to 3 Hz. Aromatic systems, 7 to 9 Hz, ortho coupling, 1 to 3 Hz, meta-coupling. The next question is question number 59. How can we use PMR spectroscopy for identification of organic compounds? Explain in detail. The answer to this question is, PMR spectroscopy is used to identify organic compounds by providing 1. Number of signals, determines the number of different proton environments. 2. Chemical shifts provides information about the types of protons, example aliphatic, aromatic, hydroxyl. 3. Integration helps calculate the relative number of protons in each environment. 4. Spin-spin coupling reveals information about how protons are connected. 5. Coupling constants helps identify geometric isomers and confirm structural details. By analyzing these features, one can deduce the molecular structure of an unknown organic compound. The next question is question number 60. How can we use PMR spectroscopy for determining the molecular weights of organic compounds? Explain in detail. The answer to this question is, PMR spectroscopy can indirectly help determine the molecular weight of organic compounds through quantitative analysis of the integral values of the peaks. By integrating the peak areas corresponding to different proton environments and comparing them with known standards, one can determine the relative number of protons in each environment, which can then be used in conjunction with other techniques to estimate the molecular formula and molecular weight. However, NMR is not a primary method for molecular weight determination. Other methods like mass spectrometry are more accurate for this purpose. The next question is question number 61. How can we use PMR spectroscopy for identification of products of a reaction? Explain in detail. The answer to this question is, by comparing the PMR spectra of the reaction's products with the starting materials, one can identify the reaction products based on 1. Disappearance of signals corresponding to the starting material's protons. 2. Appearance of new signals that correspond to the protons in the reaction products. 3. Changes in chemical shifts that reflect the formation of new functional groups. 4. Integration values that indicate changes in the number of protons in specific environments. These spectral changes can help confirm the identity of the reaction products. The next question is question number 62. How can we use PMR spectroscopy for distinguishing geometrical isomers of an organic compound? Explain in detail. The answer to this question is, PMR spectroscopy can distinguish between geometrical isomers, CIS strands, by analyzing their coupling constants and chemical shifts. CIS isomers typically have smaller coupling constants. J is approximately between 6 and 10 Hz because the protons are closer together. Trans isomers have larger coupling constants. J is approximately between 12 and 18 Hz due to the greater distance between the protons. Differences in chemical shift can also arise due to different electronic environments in CIS trans isomers. These differences allow clear identification of geometric isomers. The next question is question number 63. How can we use PMR spectroscopy for finding whether the type of hydrogen bonding is intermolecular or intramolecular when organic compounds can show either type of hydrogen bonding? Explain in detail. The answer to this question is, PMR spectroscopy can distinguish between intermolecular and intramolecular hydrogen bonding based on the chemical shift and temperature dependence of the hydrogen bonded protons, usually OH or NH protons. Intermolecular hydrogen bonding, protons involved in intermolecular bonding between molecules show broad, downfield signals in the PMR spectrum. These signals tend to shift to higher fields, upfield, upon dilution or heating, as the extent of hydrogen bonding decreases with increased temperature, or reduced concentration. Intramolecular hydrogen bonding. Protons involved in intramolecular hydrogen bonding within the same molecule show sharp, well-defined signals that are typically less temperature sensitive. This is because intramolecular bonds are more stable and less likely to be disrupted by external factors like temperature. By analyzing how the proton signals shift with changes in temperature and concentration, one can determine if the hydrogen bonding is intermolecular or intramolecular. The next question is question number 64. How can we use PMR spectroscopy for finding the relative amounts of tautomers? Explain in detail. The answer to this question is, PMR spectroscopy can be used to determine the relative amounts of tautomers by measuring the integration of the peaks corresponding to each tautomer. Tautomers, example K2-enol forms, often have distinct chemical shifts due to the different environments around the protons in each tautomeric form. The integral of each peak in the spectrum is proportional to the number of protons in each tautomer. By comparing the integrals, the ratio of tautomers can be determined. For example, in the case of K2-enol tautomerism, the OH proton of the enol form may appear as a distinct peak, and its integration can be compared to the K2 form's signals. The next question is question number 65. How can we use PMR spectroscopy for studying proton exchange processes in organic chemistry? Explain in detail. The answer to this question is, proton exchange processes, such as the exchange of OH or NH protons with solvent protons, can be studied using PMR spectroscopy by observing the behavior of exchangeable protons. Exchangeable protons often appear as broad peaks in the spectrum due to rapid exchange with solvent molecules, such as water or D2O. When a deuterated solvent like D2O is added, protons that are exchangeable, example OH or NH, are replaced by deuterium, which is invisible in PMR, and their signals disappear from the spectrum. This exchange behavior can be used to study reaction mechanisms and identify which protons in a compound are involved in exchange processes. The next question is question number 66. How can we use PMR spectroscopy for identification of conformational isomers of organic compounds? Explain in detail. The answer to this question is, conformational isomers, rotational isomers, can be identified using PMR spectroscopy by analyzing the chemical shifts, coupling constants, and temperature dependence of the spectra. Different conformations can lead to different magnetic environments for the protons, causing distinct chemical shifts. Coupling constants, J values, can change between conformers due to changes in bond angles and distances. Temperature-dependent NMR can be used to observe dynamic conformational changes. At low temperatures, different conformers may be resolved as distinct sets of peaks, while at higher temperatures, these peaks may merge due to rapid interconversion. For example, in cyclohexane, the chair and boat conformations can lead to different chemical shifts for the axial and equatorial protons. The next question is question number 67. What are the limitations of PMR spectroscopy? Explain in detail. The answer to this question is, while PMR spectroscopy is a powerful tool for structural determination, it has several limitations. 1. Complex spectra. For large or complex molecules, the spectra can become crowded and difficult to interpret, especially with overlapping signals. 2. Limited sensitivity. NMR Generally, infrared's relatively large amounts of sample, milligram to gram scale, for accurate analysis. This can be challenging for very dilute or small samples. 3. Non-NMR, active nuclei, only nuclei with non-zero spin, such as 1H, C13, can be detected. Nuclei with spin equal to 0, like C12, do not give NMR signals, limiting the study to specific isotopes. 4. Low resolution for large molecules. As molecular size increases, the spectra can suffer from low resolution due to rapid molecular tumbling, making it harder to distinguish individual peaks. 5. Infrared for deuterated solvents. To avoid interference from solvent protons, expensive deuterated solvents, example D2O, CdCl3, are often required. 6. Spin-spin coupling complexity. Interpretation of spin-spin coupling can be complicated, especially in molecules with many non-equivalent protons, leading to complex splitting patterns. 7. Solubility issues. NMR infrareds the sample to be soluble in suitable solvents. Insoluble samples cannot be studied directly using solution state NMR. Despite these limitations, PMR spectroscopy remains a crucial technique in organic chemistry and structural analysis. I hope this video will help you in learning the NMR, or specifically PMR spectroscopy, in easy and simple way without much efforts. If you enjoyed and liked the video and also wish to have such informative and interesting videos, please like, share and subscribe. Your feedback is the only key to our improvement. Please point out anything you want or should be added in the next videos in the comment box. Thanks. And we will meet soon, most likely tomorrow, with another similar video on water and its treatment.